This is problem 86 from chapter 14. In problem 86, the skier is starting from rest at point A, traveling down the ramp to point B. We are ignoring friction and air resistance. We want to find the speed of the skier at point B. We want to compute the distance S, which is the distance to where the skier strikes the ground at point C, and he makes the jump traveling horizontally at point B. We can neglect the size of the skier, and the mass of the skier is 70 kilograms. Since this is a problem from chapter 14, we are going to use the work energy conservation law to solve this problem. We have kinetic energy at point A plus gravitational potential energy at point A plus the work done as we go from point A to point B is equal to the kinetic energy at point B plus the potential energy at point B. The kinetic energy at point A is 0 since the speed at point A is 0. We have gravitational potential energy at point A, and let's say that the height is 0 here, so the height at point A is 50 meters. We have no springs in this problem, so elastic potential energy is 0. If we look at the work done by forces other than gravity and the force of the spring, in this problem we have the normal force, and we are ignoring the force of friction. The normal force does not do any work as the skier goes down the slope, since the normal force is perpendicular to the direction that the skier is traveling in. So we have kinetic energy, which is 0. We have gravitational potential energy, which is not 0. We have no elastic potential energy, and the work is 0. So on the left-hand side of the equation, we just have the mass times g times the height of the skier. On the right-hand side of the equation, we have the kinetic energy at point B, gravitational potential energy at point B, where we're going to use the height of 4, and no elastic potential energy. So we have 1/2 mvb squared plus mg times 4. Since the work done is equal to 0, we can set this equal to this and solve for the speed. Now, as we go from point B to point C, if we were to use the work energy conservation law, we would have kinetic energy at point B plus gravitational potential energy at point B, which we already calculated. We have no elastic potential energy. If you look at the work as you go from point B to point C, the only force acting down the skier would be the force of gravity, which we do not include since we're doing gravitational potential energy. But at point C, at the moment the skier hits the ground, they still have some speed, and we do not know the height at which they hit the ground. So we would have two unknowns on the right-hand side of the equation. So using the work energy conservation law would not give us enough information to find the distance. So instead of using the work energy conservation law to find the distance S, we are going to treat the rest of this problem as we go from point B to point C as a projectile motion problem. We can use equation 12(5) for this. You can write it out in vector form, and if you bring S0 over to the other side, this says that the change in position is equal to the initial velocity times t plus 1/2 the acceleration times t squared. We can draw this as a vector diagram. So here we have our initial velocity times t vector, and our acceleration vector is pointing straight down. That goes from here to here. That is 1/2 g times t squared. Our displacement vector connects the two. That's going from here to here. But rather than drawing that displacement vector going straight from here to here, we can break it up and say, in the vertical direction, we have the 4 meters from the distance that we have here. And the y component of s, if this angle is 30 degrees, would be s times sine of 30 degrees, and the x component would be s times cosine of 30 degrees. Then you can set your horizontal components, which would be this, and since the acceleration vector is pointing straight down, we just have our velocity vector, which is going in the horizontal direction, so these two must be equal to each other. That allows us to find time. And in the vertical direction, we have 4 plus s times sine of 30 degrees is equal to the 1/2 times g times t squared. That gives us this equation here. If we already solve for time, so that we can put that in here. And then we can solve for s, and since s must be positive here, that would be the positive solution, which is 131 meters. If you don't want to draw the vector diagram, you can go back to equation 12(5), and you can do this equation for the x components and for the y components and use that to find the distance s. So that concludes problem 86.